Okay. So, good afternoon, everybody. It's a pleasure to have here Patrick Eggenberger for our colloquium of our series at INAF Observatory of Abruzzo. Patrick is a senior lecturer at the University of Geneva. His research is dedicated to the development of stellar physics and evolution based on direct observational constraints obtained on the physical and dynamical properties of star interior, together with the application of these new stellar models in various astrophysical contexts. So, Patrick, as I told you, I will warn you 2 minutes in advance. And thank you very much for being here, and you can start. And please take the full screen if you... Okay, thank you.
So thanks a lot for the invitation. I will go full screen. Do not hesitate to tell me if it does not work fully. Is it okay like this?
It's okay,
Yes.
Thank you.
Okay, so thanks a lot for the invitation. So it will be a pleasure to discuss a bit the evolution of stars with both the effects of rotation and magnetic fields. So the first idea is to say, why do we need, in fact, to take into account these effects? So first of all, it will be, of course, a very biased presentation. So it's not a review. I will just give you some indication about what we are doing, especially here in Geneva. But of course, it's the illustration of this kind of effects of rotation and magnetic fields. So the first idea is to say, okay, why do we need to take into account rotation or magnetic fields? The basic idea is the following. If we are looking to standard stellar model, for instance, for the B-type star, so a massive star, we think about 10 or 15 solar mass stars. On the main sequence, this star will be mainly characterized by a convective core, and then you have a radiative envelope. So historically, what is interesting is that for the spectroscopic abundances at the surface of this star, we see some abundances that are difficult to discuss within the framework of standard stellar models. For instance, you have here the boron abundance on the vertical axis, normalized by the initial boron abundance, and here you have the abundance of nitrogen divided by the natural number of carbon compared to the initial value, so when we say initial, at the dams. So if you have a standard model which is indicated here, you would not expect any transport of chemicals in the radiative zone that is seen as being a quiet zone without any turbulent transport. So this means that you will have, of course, change in the chemical composition in the central part of the star due to the nuclear reaction, but you do not expect to see at the surface of these stars the consequences of this change in abundances due to the nuclear reaction, and for the massive star in particular, the CNO cycle. While for these massive stars, if we look at the surface nitrogen abundance, we see some enrichment of these abundances together with some decrease of the carbon abundances. So this means that instead of staying here at zero, the star can a bit shift to the right when you see enhanced nitrogen depleted carbon, which is exactly the hint of what happens with the CNO cycle. So if we see this means that we have to transport, in a sense, material from the central region of the star to the surface, which is not possible in a standard stellar model if we do not take into account some additional transport of chemicals in the radiative zone. In addition to the surface abundances of nitrogen in massive star, we also have the indication of some mixing, for instance, in the sun with the lithium abundance. So if there is no transport at all in radiative zone, you will not see a lot of lithium depletion in the sun. And for our massive star, we have the equivalent, if I may say it like this, boron that could be also destroyed close to the surface of the star if we have some mixing in the more external layers. So this is exactly what is illustrated here. If we have a standard model, we could only explain one point. If you want the star on the main sequence, we just stay without boron depletion, without change in nitrogen, while, as you see here with recent paper by Jean and collaborator, you have a large depletion in the boron abundances at the surface of the star, which is another indication that some transport of chemical elements must take place in this star instead of having simple radiative zone without transport of chemicals. So this means that we need physical transport of chemicals. So what is the physical nature of this transport? And one historical idea was to say, okay, we see that these massive stars can rotate, and they can rotate also quite fast. So what you see here is the projected velocity obtained by a spectroscopy as a function of the spectral time. So if we are looking at 9 or 20 solar masses, you see that you have a lot of stars here with a lot of dispersion. So you have very slow, at least for the projection velocity rotator, but you can have also, here you see some indications. So this is the critical velocity at the 0 age mean sequence, and this is the critical velocity for the Geneva models close to the terminal age main sequence or at the end of the main sequence. So we see that we have a lot of stars that can rotate quite fast with velocity above, for instance, 200 kilometers per second. And this means, okay, we see that these stars are rotating. So what could be the impact of rotation in these stars? And more importantly, for the relation with the chemical abundances, could additional transport processes be related to the fact that these stars are rotating? So how can we model this? So this is, as I mentioned before, a bias presentation. So I will just explain to you how this could be included in stellar evolution code by relying on what we are doing with the Geneva stellar evolution code, but this is something that could be more general. The idea is the following. If the star is rotating, we could trigger additional transport processes. One important process is first what is called meridional current. So this means that you can have, and this is just an illustration here, you can have large cell of circulation that is related to the fact that the star is rotating and you have to transport some heat inside your stars. And this could be done either clockwise or anti-clockwise. And depending on the sign of this velocity, you can either transport, for instance, angular momentum from the central region to the external region, or from the external region to the central region. We will come back to this kind of thing. The key point here is related to the fact that you will have the transport of angular momentum. This will create, if you want, differential rotation that will trigger some additional turbulence that is not present, if you want, in non-rotating stars. So you have turbulence. And of course, due to the stratification, it will be more difficult to move cells, so chemical elements, vertically than horizontally. So this is the key hypothesis that we are using here to include the effect of rotation, is to say, okay, we can have some turbulence related to the instability of rotation, but of course, it's much more easy for matter to go along horizontal, if you want, surface, or along the shells, than vertically. So this means that we have a turbulence that is highly anisotropic, and it's much, much stronger in the horizontal than in the vertical direction, due to the stratification, both thermal stratification and chemical stratification. And with this, we can say, okay, the angular velocity, which is represented by omega here, but this is also true for the, if you want, the chemical composition and so on, is approximately constant on isobar. And this is a very simple hypothesis that enables us to include easily these effects of rotation in 1D stellar evolution code, because you will have that every quantity will only depend on the radius, which is a characteristic radius of the isobar, even if the star can be a bit deformed. And within this framework, we have two terms. So this is for the transport of angular momentum. We have one term, which is advective term that depends on the meridional circulation velocity that you see here. This is the vertical component. And one term, which is a diffusive part of this equation that can be related to the different instability that we are accounting for. And in particular here, you will have the shear instability that is responsible for the transport of both angular momentum and chemicals. So basically speaking, if we go back to the classical, I would say, equation for stellar structure, what we have to do in this case is, in addition to the classical structure equation, we have to solve another equation, which is this one, in order to predict the evolution of the internal rotation profile according to the transport of meridional currents and the turbulent processes, in particular, the shear instability. Okay, so then we have to model, of course, this turbulence. So the first term that we need to know is the coefficient related to the shear instability. So in this case, we use a shear instability that is related to the work, original work by Suzanne Talon and Jean-Paul Zahn in 1997. The interesting point when you do this is that you have this kind of criteria that depend directly on the gradient of velocity in your star. So simply speaking, of course, if you have the shear instability, if the rotation profile is very flat, the transport will be inefficient, while when you increase differential rotation, which is related to this term, you will have more efficient transport of both angular momentum and chemicals. And there is one very important point here, is that we have an inhibiting effect of the chemical stratification. And mu here refer to the chemical part of the Brun-Weisseler frequency, which is related to the inhibiting effects of the transport in the vertical direction due to the chemical stratification. And when we do this, you can directly relate to this hypothesis of horizontal turbulence to find, if you want, a physical process to decrease this inhibiting effect of chemical gradients. So this is a very important advantage of having this fully advective diffusive scheme, which is much more, if you want, physically related to this horizontal turbulence that what can be done, and this is something that you will see, for instance, in the full, I would say, diffusive scheme, when you have to account for a reduction, which is arbitrary, of this inhibiting effect of chemical gradients by usually simply accounting for a very low efficiency of these gradients. So having said this, we have, of course, a very important free parameter in this formalism, which is related to the horizontal turbulence. I will not go in detail about the equation, but the basic idea is the following. You know that horizontally, the horizontal turbulence should be very efficient, much more efficient than in the vertical direction, but simply speaking, we don't know the amplitude of this turbulence, which could be seen as a free parameter. So this is really a free parameter of this formalism, but then this free parameter will reflect directly on the transport by the shear instability, the diffusive transport, but also on another very important aspect for the transport of chemicals, which are the transport by the meridional current that we have seen before. And within this framework, what is interesting is that we can show that the transport of chemical due to meridional circulation plus this horizontal turbulence can be mimicked by an effective diffusing coefficient that is purely diffusive, and that is given by this formulation. So once again, we have the DH, the coefficient for horizontal turbulence that we don't know, if you want. This is a bit of free parameter that will impact the vertical transport of chemicals by meridional circulation plus horizontal turbulence. So to understand a bit why we can have, for angular momentum, we have to fully solve the vector diffusive equation, while in the case of chemicals, we only need a diffusive equation, purely diffusive equation. We can see this. We have here the advection, if you want, that is symbol here of chemical. So we have a region with a change in the chemical composition. And this is purely advective. This is a manual circulation. But we have also to account for very efficient horizontal mixing. So then you will advect, then you mix horizontally. Once again, you advect, you mix horizontally, you advect, you mix horizontally, so that at the end, you obtain this kind of chemical profile, if you want, inside your star, which is clearly not directly related to a physical diffusive process, but that is a result of an advective process, which is manual circulation, plus a diffusive process, which is the horizontal turbulence. And this is what is expressed by this coefficient for the transport by meridional currents. For the shear, we also rely on the fact that it's a turbulent process, hydrodynamical turbulent process. So according to numerical simulation, we see approximately the same efficiency of transport for angular momentum than for chemicals, so that for the shear, we obtain the same coefficient, the diffusion coefficient, for both chemicals and angular momentum. So this framework has been historically used a lot, especially in Geneva. We computed a lot of models within this framework of cellular rotation to see the impact, for instance, on the tracks in the HR diagram, and in particular on nitrogen, because of course you add this kind of turbulent processes. So this means that you are able to explain the fact that at the surface of the star, you are enriched for the massive star in nitrogen. This has a large consequences because you change the mixing, you change the ratio, for instance, of blue to red supergiants. You can change the ratio of Wolf-Rayet to O-type stars. So all these rotating models have been used in very different contexts. They have been used also for to predict the yields of these massive stars, and you see the difference between a model. I will not go into too much detail, but it is just to say, okay, the prediction for the yields will be, the chemical yields will be different if you have non-rotating stars or fast-rotating stars. This has also been used in the context of primary nitrogen, because when you have some mixing inside your star, you are able at low metallicity to predict that you produce some primary nitrogen that could be of very interesting, in the context of the chemical evolution of the universe. You change also the different population of stars without rotation. It's more or less easy to form a Wolf-Rayet star, to go to the blue or the red part of the HR diagram, and so on, according to the mixing. So this means that taking into account rotation as described here, it's of course only theoretical results, could lead to quite different and important effects on stellar evolution. So the key question is to say, okay, but is it correct compared to what we observed? The key point, of course, as we have seen before, we depend and we rely on the fact that the star is rotating. The key question that we have, okay, but how can we probe really stellar interiors? Because this is what we want. We want to see the interior of the star and to test our model that describe the transport of chemicals and angular momentum inside the star. The problem, as you know, the mean free path of photons in the case of a star of the sun is 1 centimeter, perhaps, so you only see the surface of your star, which is, of course, of prime interest. So you see magnetic field at the surface or whatever, but we don't have access, you see, to really the internal part of the star, and this is exactly what we need in particular to constrain this dynamical model of star with rotation. So how can we probe stellar interior, which is a key question that is, of course, related to how do we know the internal structure of the Earth. And for the Earth, we can use earthquakes, seismology, in order to infer the internal structure of the Earth. Even in the case of a very, very powerful earthquake, you can have not only the detection of the wave, but sometimes you can have also the global oscillation of the star due to the powerful release of energy. So the question is to say, okay, we can do this for the Earth. Can we do this on stars? And the main question is, do we have quakes on stars? Is it possible to have this? And if you look at the surface of the sun, which is illustrated here, you see that you will have a lot of bubbles related to the convection in the external layers. And all this convective motion can play the role, if you want, of continuously having quakes, like earthquake on the Earth, in the sense that they will produce a lot of shocks and produce with this stochastic motion, they will excite the different frequencies of this oscillation. So they can excite this oscillation, and then by interference, you will remain with the eigenfrequency and eigenmodes of your objects, of your stars in general. But of course, we cannot put detector at the surface of the star, so we are only seeing the star. And then the idea is the following for asteroseismology. The idea is to see the deformation that are, of course, here largely exaggerated. But the idea is that due to this motion, you have different oscillation modes. So what you do is that you try to see at the surface of the star how the star can be deformed and at which frequency it can be deformed. And from this, you want to know how you can probe the interior by analysis, if you want, the deformation of the surface of the star. So, of course, it's very difficult to observe these small motions, and this has been possible first in the case of the sun with what is called helioseismology. And in the context of evolution with rotation, we then obtain very, very powerful and insightful information, which is what you see here, the angular velocity inside the sun. So here you are at the surface of the sun, and here we go to the center of the sun. And what you see here is that in the convective envelope, you have some differential rotation as a function of the latitude, as we know at the surface of the sun. But then, in the radiative interior, a striking feature of the sun is that the rotation is more or less solid body. It's very flat, and it does not depend on latitude. So this is a first very important constraint that, of course, our model with rotation must satisfy. And what happens if we compute a model? So we start here for a solar model. So this is the angular velocity inside our model. We start with a flat rotation by assuming a flat rotation profile on the ZAMS. We let the model evolve according to the framework, theoretical framework, what we have seen before. And in blue, you have the profile at the edge of the sun when you see that the core is rotating 20 times more rapidly than the surface, which is in complete contradiction with this flat rotation profile. So clearly, from helioseismology, we know from years that within this framework, we have a problem. The transport by only meridional currents and shear instability is inefficient to explain the flat rotation profile of the sun. So this is the first indication here that we are missing a very efficient transport process for angular momentum. The key question, of course, is to say, okay, is the sun a special case, or the massive star we were discussing before, or more evolved star, they behave in the same way? We don't know. So the idea is the following. We need to go from helio to asteroseismology. So the idea would be, okay, are we able to obtain some information about the internal dynamics for other stars than the sun? So historically, we have first obtained information from the ground for some stars, so it's difficult to obtain for, at least for solar-like oscillation, it's difficult to have the internal rotation of this star, but for some beta Cepheid, you have some historically some detection from the ground. But here really the revolution comes from space with the observation of a very large number of stars for which you have asteroseismology, and for some of these stars, in particular for the red giant. So what you see here is the luminosity, so it's not indicated as a function of the effective temperature with low temperature here. So this is the HR diagram. And you see here a large amount of red giant for which we have asteroseismic detection with Kepler in this case. So we have here a lot of stars for which it's possible to do this asteroseismology. And very interestingly, we obtained more than 10 years ago the first detection of the rotation in the very central layers for an evolved red giant star. So in this case, what is interesting, by the way, is that we can obtain the rotation in the core of the star due to the different structure of the star on the main sequence and after the main sequence. If the star is more condensed, you can have what we call mixed mode in asteroseismology, so mode that behave like gravity mode in the central region and pressure mode in the external region. And this is interesting because in the case of the Sun, as you have perhaps noticed here, we are still missing a very powerful constraint that could be obtained by detecting the gravity mode in the Sun, which is a difficult quest. But as you see here, we don't know exactly, and this will be a very powerful constraint, by the way, as we will see in a few minutes, to have the rotation in the very central layer of the Sun. While for this red giant, what is interesting is that due to the different structure with a very dense core and extended diffuse envelope, we are able to detect the core rotation rate. So I will not go into too much detail, but this is what is called rotational splitting. You see the prediction if the star will be rotated as a solid body, as the Sun. And directly observations show that instead of this shape, we have a V shape. And from this V shape, we can say, okay, we know that the core is rotating more rapidly than the external layer. So this is clear from the beginning. Then we can try to go in a bit more detail to obtain the core rotation rate. And we see in this peculiar determination that the core is rotating approximately 10 times more rapidly than the surface. So at first we can say, okay, we see differential rotation. Model with rotation only predict this differential rotation. So are we in good agreement? And this is the comparison we perform thanks to this data. So we just compute model with rotation as described before, and we compare with observation. So we have differential rotation for this red giant, but model with rotation only will predict very high rotation rate, which is completely incompatible with asteroseismic data. So instead of a factor of 10, we have a factor of 1,000. So this means that we are 2 or 3 orders of magnitude higher than what is seen by differential rotation. So this is a very important point because we see that for these red giants, we also need an additional efficient transport of angular momentum, which is similar to what we have seen in the case of the Sun. So once again, models with rotation only are not correctly reproducing the internal rotation of the Sun, but also of red giant, sorry. This is also the case for the subgiant. What is represented here is the ratio between the core and the surface rotation rate as a function of the log of gravity, which is a proxy for the evolution of our star. We don't have a lot of subgiant stars. These are stars that have typically masses between 1.2 and 1.5 solar masses. So they are during the subgiant phase. We see the models, and typically we are already at 1 or 2 orders of magnitude higher in differential rotation compared to observation. So once again, we need an additional transport process for angular momentum for these stars compared to what we described before with hydrodynamical processes only. A key point that we can do is that we can use, in fact, these asteroseismic data in order to characterize, if you want, the efficiency of this additional unknown process. And what we find in this case, this is what is indicated here by introducing an additional viscosity, which is an arbitrary viscosity that is representing what should be the efficiency of the unknown transport process in order to correctly reproduce the asteroseismic data. And an interesting conclusion here is that during the subgiant phase, this unknown process, the efficiency of this unknown process should first decrease, and then it should increase again during the red giant branch, and must increase even more during the core helium burning, which is indicated here. So this kind of characterization, thanks to asteroseismic data, can be done as a function of a diffusive process. But if you prefer to have non-diffusive process, for instance, transport by waves, you can also evaluate the flux of angular momentum that is needed for the same star that we have seen before. So this is just to illustrate here that thanks to asteroseismic data, we know that we are missing something, and we can, if you want, estimate a bit the efficiency of the transport process that is needed. And then, of course, we will try to find the physical nature of this additional process and compare to these observations. So the key points to keep in mind at this stage is that we have seen before that we need some additional transport process. We rely on rotation to say, okay, this can explain the surface enrichment, but then when we go directly to the physical nature of this process, so the internal rotation, we say, oh, we have a problem. The current generation of models cannot correctly account for the internal rotation of stars. So this means that we need an additional transport process, and this is why I will shift to the second part of this presentation dedicated to magnetic field. So we are not just making evolution with rotation, we are also considering magnetic field. There are other possibilities for these efficient transport processes, for instance, transport by internal gravity waves, but in this case, I will present a process that is missing in the above description, which are magnetic fields. And in particular, we'll talk about magnetic instabilities. So the idea is the following: if you have magnetic fields, it's not so easy, in fact, to find a stable solution. So one of the main challenge was to be able to find a solution that is compatible for what we see for some star for which we detect a large dipolar and large scale, very strong fossil field. So this is possible by combining, if you want, toroidal, poloidal field, but it's not so easy. Why? Because when you have strong toroidal or purely poloidal field, these fields are easily unstable. And this leads to an interesting thing, that if you evolve a star and there are some differential rotation, you can quite rapidly wind up this line and create very, very rapidly strong toroidal field, so field in the horizontal direction from this line. So very rapidly you can have very strong toroidal fields that are then unstable. This could be either unstable with the Taylor instability. We have also what is called the magnetorotational instability. So you have different kind of magnetic or magnetic plus rotation instability. And I will focus here only on these two main instability, because they can lead to very interesting transport process that are efficient for the transport of angular momentum. So this is perhaps an interesting candidate for solving the problem that we have seen before for the angular momentum. So we have two possibilities, I would say the Taylor instability and the MRI. This was first introduced by Sproit in 2002, but then in the community there were a lot of debate about the very existence of these processes, especially because there are different results depending on numerical simulation. There were simulation saying that it's not possible, and another one saying it is possible, but under very, I would say, optimistic and non-very realistic stellar condition. For the MRI, this is something that is well known, but it requires strong shears, and sometimes it can be quite inhibited by what we have seen before, the chemical gradients. The main change has been, sorry, I will perhaps, yes, I will just show this. The main change recently come from numerical simulation that have confirmed, and this is a very important result, that we can have a dynamo, some kind of small-scale dynamo in the radiative zone of these stars based on the Taylor instability as originally introduced by Sproit and collaborators. So this is a very important result that are really recent by Ludovic Petit-Demer in 2023, also simulation by Paul Barrère to confirm this, but the global view, okay, it is possible to have this kind of process operating in stellar interiors. So we have to account for this process, and this is done. I will not go into too much detail, but the key point is the following. Within the framework that we have seen before, we will add some additional transport process that is only effective above a given threshold for the instability to set in, and this threshold is given by the degree of differential rotation. If you don't have enough differential rotation, you are not able to have this instability, so you need some differential rotation. And then you have the relation with an efficiency for the transport of angular momentum that is given by this viscosity associated to magnetic field. This is the same for the magnetorotational instability. You can have the prescription for the transport. And all these is added in the equation that we have seen before for the internal transport of angular momentum. And then we will solve, if you want, these transport processes and see the impact for the evolution of our star, in particular for the internal rotation of the star. So this, of course, has first been done in the case of the Sun. So for the Sun, what you see here is this is the angular velocity, function of the radius. These are the helioseismic data. As we have said before, with rotation only, we have very strong differential rotation that is incompatible with this data. Well, with this process, we are able to correctly represent this. Then, you see, we can have, depending on the prescription, if it's the original Taylor's point, we see that we have a core that is rotating approximately 4 times more rapidly than the surface. This change, by the way, in the rotation profile is directly related to the fact that here you have strong chemical gradients related to the nuclear reactions. So this will decrease the efficiency of the transport and leads to this. And depending on the exact modeling, either the original prescription or the revised prescription by Fuller and collaborator in 2019, you see a very strong difference in region with chemical gradients. And of course, this will be very interesting, as I mentioned before, to obtain a definite answer. These are reported detection by Fossat and collaborator and by Garcia and collaborator, but there are no confirmation yet about the core rotation rate of the Sun. So of course, if the Sun is here or here, it changes a bit, and it will help us progress in the modeling of this magnetic process, which will be, of course, of interest for the Sun, but not only, because it will constrain, the transport in region with strong chemical gradient, which is exactly what we have for more advanced phases of stellar evolution. So we see that these models are in better agreement with the Sun. This is also the case for solar-type stars. We know we begin to have some constraint from rotation due to asteroseismology, plus an independent measurement of the surface for some solar-type star on the main sequence. We see that with rotation only, we predict too much differential rotation to be compatible with asteroseismic data, while with magnetic field it is better. This is the same for what we call gamma Doradus pulsator. They are typically a star between 1.5 to solar masses on the main sequence. And what you see here is the surface velocity, projected velocity as a function of the near core. We can detect what is called the near core rotation rate. And we see that with rotation only, we predict too strong differential rotation to be compatible with this data. So once again, we see that for this star, we need an additional efficient process, and that with this kind of magnetic field, we are in better position to reproduce this constraint on the main sequence. Of course, the key challenge is to reproduce what we have seen before, the rotation rate for evolved star after the main sequence, when you have a fast contraction of the central layer, so you need to transport quite efficiently angular momentum. As we have seen before, this is the same plot as before, the ratio of core to surface rotation rate as a function of log G. Without magnetic field, we predict too high degree of differential rotation. While with this kind of magnetic process, it is better, but it is not perfectly reproducing all the data. In particular, what you see here, we have the core rotation rate for a large number of red giants. So we can reproduce this with a magnetic field, but then there is incompatibility with these subgiants that show a higher degree of differential rotation. So you see a bit what we have here. We have better solution, we can have some better agreement, but this is not optimal. What is very difficult currently is to find a physical process that can reproduce all the data that we have for our stars. And this is the same for the magnetorotational instability. It can play a role. We compare to what we have seen before and we see what's going on. I will not enter into too much detail, but we have a better agreement when we include magnetic fields. So the question is now, what are the consequences for the more massive stars? And you see here the rotation profile for a 15 solar mass star. So this is without magnetic field. You predict high degree of differential rotation, while here with magnetic field, you have solid body rotation almost. And then when the star is approaching the end of the main sequence, you have more chemical gradients. You see some small differential rotation. So we see a difference with magnetic field. As expected, the rotation rates, the rotation profiles, sorry, are flatter than without magnetic fields. And this has, of course, key consequences for the advanced phases. And in particular, I will focus here on a result that is known from a long time ago, is that with rotation only and without magnetic field, we do predict rotation rates for neutron stars that are too high compared to observation, while when you include this process, you are in better agreement with for the neutron star, the rotation rate, while for white dwarf, you see that you are in better agreement, but still predicting a bit too fast rotation for the white dwarf. So we see here the connection between what we see from asteroseismology and the rotation rate in the final stage of the evolution. The key point, and if I still have 5 minutes, do not hesitate to interrupt me, it's a bit too long, it's just to say, okay, we have seen here that we are focusing on the transport of angular momentum, but what is the consequence for chemical elements, and how can we derive, if we want, develop models that are compatible with both what we see from asteroseismology for the internal rotation, but also for the chemical transport. And for this, of course, we have to include, I will not enter into too many details, but we can also infer within the same theoretical framework that we have seen before, the impact of magnetic field on the transport of chemical. And there is also the indirect transport of chemical, because if you change the rotation profile, you will change also the transport by other hydrodynamical instability, like the shear instability is decreased, transport by manual currents are increased, for instance. And what is the consequence? For instance, for the sun, what is interesting here is to look at, as we have said in the introduction, the lithium abundance. What we see with standard model, we have some depletion during the pre-main sequence, but then it's more or less flat because we don't have transport processes during the main sequence. If we have rotation only, this is shown here, we deplete very efficiently lithium, but at the edge of the sun, we cannot reproduce the observed lithium abundance because we deplete more or less all the lithium during the main sequence. While with both rotation and magnetic field, we are able to have something intermediate between which, okay, we have a differential rotation, but is very moderate, and so this introduces a small transport of chemical that is able to reproduce the lithium in addition to reproducing, as we have seen before, the rotation profile as deduced from hydroseismic data. So this corresponds to encouraging result in, if you want, the goal to have something that is coherent from the point of view of angular momentum and chemical elements. But of course, if we use this model for massive stars, we see a huge difference. So what is illustrated here, this is the HR diagram for a 15 solar mass model without a rotation. This is the black line here. Same model with only rotation as described before, and exactly the same input parameter, but with magnetic field. And you see that, perhaps contrary to what we could anticipated, we see that
you have 5 minutes.
Okay, so I will go for the 5 remaining minutes on this topic. So what you see here with rotation plus magnetic field, that even if the star is rotating much more approximately like a solid body during the main sequence, you also have a strong chemical mixing. But this time the mixing is not due to the shear instability, it is due to the fact that the meridional currents are quite far from the being in an equilibrium phase. So this increases the transport of chemicals. And this can be seen as a function of the nitrogen abundance. So once again, we have also to develop models that are able to correctly reproduce the surface nitrogen abundance in addition to reproducing the asteroseismic constraint on the internal rotation. And this can also be done thanks to asteroseismology, because we also can use, for instance, SPB stars. So these are typically main sequence stars with 6 solar masses, 8 solar masses for the mass range. And we can also use asteroseismology in order to constrain directly what we see here. This is the abundance profile of hydrogen in the central part of the star. So we can use also asteroseismology to try to see also what is the mixing close to the core of the star, which can give us also additional information. Of course, it's a bit difficult because it could be due to overshooting, to other processes, but it can give us also additional information about transport of chemicals. These have also a lot of consequences for the remaining 3 minutes, I would say. I will just illustrate this. If you think about binary stars, of course, if you have a mixing that is more efficient with magnetic field, this means also that you can have more easily chemical homogeneous evolution. So you can perhaps avoid some mass transfer, some common envelopes. So you change a bit also the formation channel of a different kind of processes that are related to binary stars, for instance. This is also the same for the evolution of planetary system. I just want to finish here by illustrating this. Of course, depending on the internal transport of angular momentum, you will change a bit the rotation velocity of the star. So this is illustrated here for one solar mass star. You have the model with magnetic field here, fast rotating, model without magnetic field. And due to the fact that you are able to break more rapidly the surface without magnetic field, you will also change the X-ray fluxes received by your planet. So this means that all the magnetic and rotational property can be followed within this framework, and this has some consequences for the X UV flux received by the planet. So this will change the evaporation of exoplanetary atmosphere. It will change also the dissipation by dynamical tides. So this means that we are also using this in the context of the upcoming Plato mission to develop, if you want, a global framework to follow the global evolution of planetary system, but this time accounting for this magnetic and rotational evolution of the planet host star with 2 key features: change for the evaporation of the atmosphere, change of the evolution of the orbital parameter of the system, and you can even have engulfment after the main sequence by your red giants. And this is just an illustration here, is that when you engulf a planet, you can explain some very fast rotating, very fast for red giants, and we are talking about stars with 15 kilometers per second for the velocity, but these stars cannot be explained by single evolution, even if you are at critical velocity at the beginning. So this means that if you have fast rotating red giant, this is interesting. This means that you have an interaction, and one possibility to account for this is to have the engulfment of a planet due to the tides when the star becomes a red giant. So I think I will stop here. The idea was just to say, as a summary, that we want to try to improve, as you have seen, the modeling of these effects of rotation and magnetic field, and we rely for this on asteroseismic data. So this is done basically with Kepler data currently. We are waiting for the upcoming Plato mission. Perhaps there will be, if we are lucky, the Haydn mission, which will be proposed as the next call M8 for the ESA. Call, and we use all these asteroseismic data to try to improve our modeling of transport of angular momentum by magnetic but also hydrodynamic processes. And we then try also to rely this to, as you have seen, some validation by 3D numerical simulation to obtain models ideally with a coherent transport of angular momentum and chemicals, where they are coherent physically, but they are not necessarily correct. And then we want to use it either, of course, to predict what is going on at low metallicity, to have, if you want, the evolution of the chemical evolution of the universe, or the question of the first generation of stars, but also in connection with the star-planet interaction. So I will stop here. Thanks a lot for your attention. Sorry if I was a bit too long.
Thank you, Patrick. Thank you very much. Thank you. Are there some questions? Just unmute yourself if you want to speak.
May I ask some?
Please go ahead, Santi.
Okay, thank you. Many thanks, Patrick, for this very comprehensive talk on rotation. I have some curiosity and one comment. The curiosity is this one. You have shown clearly that rotation is not enough. We need to include some additional mechanism in order to extract angular momentum, in order to put the model in agreement with the main asteroseismic constraint for the Sun and the giant branch star. And you have shown that including magnetic field can help, and it seems to help a lot. But if I remember about 20 years ago, concerning in particular the case of the Sun, there was a nice work made by Susan Talon that showed that the same result could be obtained including internal gravitational wave as a mechanism to extract angular momentum. But I don't think that there's been any follow-up of this investigation for giants. So the point is that internal gravity wave could be also a solution in this topic.
Yes, this is a very interesting point. I would say that for the Sun, what we see with the work by Suzanne Talon is that you are able to extract angular momentum from the central region. But if you want, this is done with propagation fronts, what we see in the data with Suzanne. So at the end, you obtain a profile that is in much better agreement than without internal gravity waves. But when we compare with very, you see, precise helioseismic data, the change in omega are too high. So there is a paper by Pavel Denisenkov in 2008 for this to say, okay, it's a bit better, but it's still, since it's not a diffusive process, of course, by itself, it's a bit difficult to reproduce exactly the flat rotation profile of the Sun. This is the first point. And the second, for the red giants, there is a work by Charlie Pinson and collaborator to show that you can reproduce the subgiant, but after, it's not possible with these gravity waves because they are facing the huge chemical gradient that we have at the border of the helium core. So if you want, the wave will be very efficient for transporting angular momentum in the external part, but they cannot enter into the core in order to extract it. So there is some kind of moment whether you don't have a transport, but then according to a result by Kevin Belkacem and collaborator, you can also have the transport not by evanescent waves, but by the mixed mode oscillation modes. But it is for more luminous red giants. So simply speaking, this means that with gravity waves or internal gravity waves, you can explain and you have an impact on the main sequence during the subgiant phase, but you will be, at least for the formalism we know at the moment, have to be careful. It's difficult to explain the core rotation rate of red giant, which is the main challenge, if you want, here.
Yeah. Okay. And the other question is, you have shown in one plot the impact in the Esmond-Russell diagram for a model. I don't know the mass of that model. I don't see any label. Whether is the model not rotating one, only rotation and rotation plus magnetic field.
It was a 15 solar mass star, I think.
And I saw that the impact on the Esmond-Russell diagram in the turn-off region is really dramatic. So in some sense, we could also use the morphology of core magnitude diagram in young cluster to discriminate about the efficiency of this mechanism, no?
Yes, this is a key point. This is why I highlight the need to have a coherent transport of angular momentum and chemicals. What we have to remember is that we have this free parameter, which is the horizontal turbulence in our formalism. So this means that if you want, we have to recalibrate somewhat the transport of chemicals to reproduce the nitrogen abundances, because what we see with this kind of plot, I don't know, I will try to, sorry, I will try to go back. This was this plot, I think. What you see here is that this is a 15 solar mass star, so you have a huge change in the HR diagram, but this is also, and this corresponds to this model here, the red line, it's a bit too much for nitrogen enrichment in the middle of the main sequence. It's in the upper part. So this means here that we are a bit over predicting, if you want, the transport of chemicals. So we have to decrease it through the horizontal turbulence. So effectively, it's important, but the key point is the following. Once this is done, either for the lithium board, we cannot change it. So this is effectively very important because we will change if you want, the chemical enrichment. And then, as you mentioned, you will change also the turn-off and all what we see on the HR diagram. Yes, the key point is that the change that you see here in the HR diagram is also due to the mixing close to the border of the core. You see, so you will not necessarily, and this is something that it's a bit more difficult to characterize, that you can have in the same model more mixing in a given region, but less mixing in the external layers, if you want. So this is what we see with magnetic field. We have less mixing in the external layers, so less lithium boron depletion, for instance, but an increase of the size of the core and more mixing close to the border of the core that translates in a more chemically homogeneous evolution, if you want. Even if the surface abundances can be, you see, different.
Okay. I would have another curiosity, but I don't know if there are other persons that want to ask a question. So eventually I postpone my.
I don't know if someone wants to ask. Okay, you can go, Santi.
Okay, no, I have just a curiosity. I think that in the field of rotation of star, one of the most interesting results obtained but the case of asteroseismology has been the discovery made by Baer in his doctoral thesis, the doctoral work at the end of last century about the rotational bimodality in horizontal branch star in globular cluster. The fact that the star hotter than about 14,000 degrees were extremely slow rotator and cooler star were faster rotator with VCI around 20 kilometers per second. And if I remember, there was only the attempt by Pinzonot to reproduce this bimodality with a very poor result. It was impossible to match this pattern in the rotational velocity. Do you know if there have been any work on that, or you have personally done something in this kind of evolved star?
No, I have to say that I don't know exactly. So this seems to be difficult to reproduce effectively, but yes, no, I'm not aware. I have to say.
But just to put, to put a stone in the water, a few years ago we have found that in the extremely hot horizontal branch star there are some indication of strong magnetic field. So maybe there is some link in that. That's it. Thank you.
Yes, very interesting. Yes, thank you.
I have a question myself, Patrick.
Yes.
Do you think asteroseismology can be exploited to infer the intensity of the internal magnetic fields, if magnetic fields are responsible for, I don't know, transport of angular momentum and chemicals?
Yes, this is a very good question. In fact, there are detection of magnetic fields, but it's very strong magnetic fields, so kilogauss. So this is very interesting because it does not correspond to what you see here, which are really small-scale dynamo that are strong in the horizontal direction, toroidal field, but not in the vertical direction. So there are some detection and indirect detection also of oscillation mode that are, if you want, damped by the magnetic fields, but these are for, I would say, some stars for which the magnetic field is very strong. And in this case, it's a bit another origin that is put forward, which is more the formation of a strong either fossil field from the beginning or a fossil field that could be also amplified by the dynamo in the convective core of these stars, because it seems that you see a difference between star with or without a convective core. So we have detection, but only a very strong internal field that are not compatible with this view. If you want, what we see here is the transport of angular momentum for star for which we know from the beginning that the magnetic field is not too high. this is really very small intensity of the field, so that the dynamic of the star can be dominating at the beginning and create the strong field by winding up the line. If the field from the beginning is very strong, it dominates the dynamic of the star from the beginning. So you don't have the winding up of the line and this kind of process. So this means that here we are, if you want, we try to model the majority of stars, but not the 10% of stars for which you see survey seems to see large-scale, strong magnetic field on the main sequence. And it could be, but this has to be, of course, shown, that the star that we see with strong internal field during the region could be related to the 10% of stars for which we see strong magnetic field on the main sequence, or this could be related to amplification by the convective core. It's difficult to say. So there are, if you want, detection of magnetic field, but this cannot directly probe this kind of process that is related to the small-scale dynamo.
Thank you. Are there any questions? More questions?
I might have a curiosity. So I come from a completely different expertise. So thank you for the presentation. It was very interesting. But anyway, so coming from the field of extragalactic astronomy, and where you don't see single stars, you've shown that to explain what we observe in single stars, these phenomena are fundamental to be included. But from the extragalactic perspective, okay, most of the time people use empirical laws, but sometimes to study their galaxies and the properties of their galaxies. But sometimes also stellar population models are used. And those stellar population models, stellar synthesis models, numerical models, they always use, standard tracks elaborated from models that do not include rotation or magnetic fields, as far as I know. So now, I have two curiosities. First of all, is this ignoring these effects? It's just producing bias, or it's completely below our errors? And so we can ignore that for the extragalactic science. And the second question is, as far as you know, is there some project or someone who's already doing stellar population synthesis with these ingredients?
Alors, of course, it depends on the topic you want to address. You see, one very interesting, perhaps, consequence is for the chemical evolution of the universe. For instance, if you have some mixing, whatever, by the way, the source of mixing, you can have the production of primary nitrogen. So this could be of interest to reproduce, to see what we see for the evolution of star, and also the fact that with the GWST, you see also from nitrogen-rich galaxy and so on. The question of primary nitrogen can be related, and of course, with standard model, you cannot address this kind of question. Then what you see here, perhaps, is also the fact that we are more chemically homogeneous. So this means that it has some consequences for the ionizing fluxes. So usually people that are doing, you see this, they will use also binary stars, but binary stars also to explain that you need also the origin of the ionizing fluxes from the stellar population for ionization of the universe. So in this case, I think it's a bit too early to say, but we have to take this into account, because the global idea is the following. With asteroseismology, we only have constraint at solar metallicity, basically. The idea is to try to have the physical description that we think is the most reliable at solar metallicity to gain some predictive power at low metallicity. And this is related to this question of free parameter that I was discussing before. If you have a free parameter that is related to a physical process, perhaps you can relate on this to extract at low metallicity. If you don't, because you don't know what is the physical process behind, and you just put a constant, then it's much more difficult to trust your model at low metallicity, I would say. So this is a bit the answer that I can make, and this is also why we have seen the consequences. I was a bit rapid on this, but if you include these different transport processes, you will also change the binary evolution, because if you want, binary will with transfer angular momentum. So the way a star is reacting to rotation is very important in this case also. So I would say that it has some consequences, and the idea is this is what we did for the model with rotation only, is to provide the community with grids of model that could be used, not necessarily by us, by the community, to study this kind of population synthesis, and to redo this once we do believe that we have a good physical description of rotation magnetic field, which is too early, I have to say. But we see some interesting consequences on the ionizing fluxes, the chemical evolution, this is clear, and this has to be investigated clearly, yes.
Thank you.
Okay, if there are no more questions, I think we can thank again Patrick. So thank again.
So thanks a lot for the invitation.
Thank you, Patrick.
Our pleasure. Thank you again.
Thank you. Bye-bye.
Bye.
Thank you. Bye-bye.
Thank you. Bye-bye.
Ciao, Patrick. Bye.
Bye-bye.
Ciao.
Thank you.
Ci stanno delle variazioni sulle proprietà osservate cruciali, cruciali da un dato relazionale. Perché proprietà fai da prova? Cioè, ci sta